All right, well, I guess I'll get started. Um, so yeah, last time I believe we ended on discussing the counterfactual mugging with evidence. So that was to illustrate this more general phenomenon that for UDT that is empirically updateless, but not computationally updateless, we have this phenomenon that we behave updatefully when it's appropriate to do so. So, updateless decision theory is not kind of stuck being updateless, but rather updateless decision theory ought to be like updateful whenever it's useful to do so. And so it strictly kind of generalizes the cases where updateful decision theory is correct. And so here I'm saying that a bit more formally, that so we can think of decomposing a decision problem into branches where like we have some partition on the space of possibilities, and I'm just calling an element of that partition a branch, like a branch of possibility space. And so we can decompose these expectations into a sum across branches of the branch probability times the branch expectation, where phi here is the thing we condition on in the decision criterion. So either an individual policy point for UDT 1.0 or a full policy for UDT 1.1. So considering UDT 1.0, if a policy point choice um, does not impact other branches, so this is a policy point for O1, or rather a choice between policy points for O1, which does not influence the expected utility of O2 or O3. That is the expected utility conditioning on the observation. And also does not influence the branch probabilities. So the probability that we end up in O2 or O3, then UDT will behave in an updateful manner. And similarly, if we do a sort of a hierarchical partitioning where we partition on, we have a coarse grain partition on some information and a finer grain partition on some other information, then we can argue that like UDT will partially update when it's appropriate. So it will update on only this coarse grained and not the fine grained information when it's like appropriate for it to do that. Hi, Roman.
Hi, sorry for being late.
Yeah, so I was just, so like the previous slide, the last slide last time, if I recall correctly, was counterfactual mugging with evidence. And the point that I was making there is that UDT can behave updatefully in certain cases when it's appropriate to do so, and furthermore can behave like partially updatefully, like act as if it had updated on some information but not other. And this is like formalizing that more. So specifying the conditions in general under which we expect UDT to behave like that. For a particular observation, the branch probability shouldn't be changed, and the expectation of other branches shouldn't be changed. So we can call these two factors. These aren't perfect names, but they're the best names I have so far. So if we're considering a policy point for O1, then the impact on O1, the expectation of like conditioned on O1 and the policy point, we could call that the causal impact, because we're just kind of going forward in time at that point. We're like, in counterfactual mugging, if Omega asks us for $10, then the causal impact of giving up that $10 would be just losing $10, right? And then the impact on the expected utility of other branches. So here, like O1, O2, and O3, we can call that the acausal impact, because we're like influencing these parallel universes in this like acausal way. And then the influence on branch probabilities, so we might make O2 more probable than O1 by taking a certain action. We could call that the retrocausal impact, because we're kind of changing history. So this would be like in a transparent Newcomb problem, for example, which is Newcomb's problem where we can see the money in both boxes so that we actually know what Omega's prediction was about it. We know that Omega predicted that we wouldn't take the boxes or that we would take the boxes. And then if we do the opposite action that we see in front of us, then we have a retrocausal influence where we like make that branch of possibility impossible.
By the way, like with there is a certain problem with I'm not sure if that is right, but I think that there might be a problem with that sort of decision problem, which is that you might stuck in a loop. Like if I see like if I see one situation, I'm going to act in such a way that this situation wouldn't be the case. If that is, you understand what I mean? Like
Yeah.
you can be the decision algorithm in such a way that there is no stable outcome for Omega to predict.
Yeah, like if we're playing rock, paper, scissors with Omega, and Omega can predict us perfectly, but wants to take optimal moves. But then also it's like the transparent case where we can see what Omega's prediction is. And so we can just take a different move than Omega predicts. So it's my view on this kind of problem is like, in general, it depends both on like Omega's strategy and our strategy to determine whether it's consistent. The ones that are like really clearly well-defined problems are when we make sure Omega's strategy is such that it's always well-defined. So for example, in transparent Newcomb, if Omega just tries to predict what we do in the raw form of like, are we actually going to take the large box or not, then our strategy can be such, like, not that we should invoke this strategy in any sense, but we could have a strategy that diagonalizes against that just makes Omega's prediction impossible. And so then it's inconsistent. Then if omega predicts we do one thing, we do the opposite. And so then we just can't end up in that decision problem. Like if omega is like this, then omega has to pass us by.
If you and omega are those kind
Right.
of, if omega can predict you and not can predict you, if it can't find a consistent way to pose this problem, then yeah, okay. The standard way in like game theory to deal with that is like to make strategies like mixed strategies and find some equilibrium. So you're seeing like with some probability.
Yeah.
Is it so? Is it even relevant? Am I raising the right question? Or
yeah, I mean it's totally relevant to like dealing with these sorts of decision problems. You need to think about these sorts of things. And what I would say for the kind of standard solution in UDT space, as opposed to this like mixed strategy and game theory, which I think is also like a way to try to handle this. But if omega's strategy is a function not of what individual action we take, but of our policy. So like omega isn't trying to look at, do you take the big box, yes or no? But rather omega is trying to look at like, well, if the big box is full, do you take it? Then in this case, that makes it well defined, because if you, so like omega is filling the big box if you leave alone, given that it's full, right? And then there's no strategy that you can take that just like invalidates what omega does.
I think I believe that Vladimir tried to paraphrase Roman in the chat. Is that right? Okay, I'll just read it out. Like abstract algorithm. Oh, okay. Okay, maybe I don't really understand the comment. But I think maybe we have time for this. Like, Vladimir, would you like to just say what you mean? Okay.
So
anyway.
you are saying that you're saying that they're gonna like their content is well defined, but all possibilities do not exist. Like so, I kind of don't get it. Sorry.
So yeah, abstract algorithm use still takes different moves for different observations, regardless of which possibilities exist. So that's like this. We're talking about this question of, well, which ones are consistent. I am drawing this distinction between omega just trying to predict whether you take the box regardless of observation, versus if omega is a function of the policy and looking at specific policy points and saying, well, what does Roman do if the box is full? So I think Vladimir is just saying that the policy is well defined regardless of which thing happens, or even if the decision problem happens at all. Like if we take some policy that makes the whole decision problem inconsistent, then the policy itself is still like,
okay. You can play this algorithm out and it plays in some way, not necessarily that the assumptions of the decision problem holds. Like the assumption that omega rightly predicts you. So okay.
Yeah. So, I guess any further questions before I move on from this slide? So basically what I'm saying is, like, this is the picture that we have with like UDT problems that we know how to think about. How can we extend these pictures to UDTs that we don't, the UDT problems that we don't know how to think about, namely those which heavily involve computationally uncertain reasoning. Like, how can we make a logical inductor powered updateless decision theory that respects decomposition roughly like this? Is this even possible, or is this going to be violating the bounded cognition too heavily?
So
And,
yeah,
yeah,
I thought you didn't fully cover the bottom half of the slides, the
yeah.
this slide.
So I didn't really formally write out this bottom half. And looking at it now, I'm like, well, yeah, like part of the reason I didn't fully formalize this bottom half is I sort of want to put like observations on these partial branches, but the way I've spelled out what observations are, they're actually all mutually inconsistent with each other in the formalism that I've chosen, because like observations include memories, right? And so you don't first observe this partial information and then observe more information. When you observe this, you also know that you're not at this branch. And so in order for this decomposition to make sense, like this needs to be a partition, and then it has a further refinement on like full observations. And so similarly, we can decompose the expectation over all of this into a sum, but and then like what I'm trying to say is something about like when we decompose this sum, we can behave partially update fully if like we don't satisfy these conditions of no acausal influence and no retrocausal influence when we look at the full information, but there's some partial information out of the information that we got in our observations, which we can consider such that the part of our policy that has this information.
I kind of see what you mean. So you're saying that if we use the middle point as the vantage point, we might be able to say like from this point onwards, the condition like the no impact conditions hold true, but this might not be true if we go further backwards.
Yeah, exactly. Or further forward, right? If our policy here impacts the expectation here and also the branch probability of this one, but does not influence the expectations here at all, and also doesn't influence this branch probability at all, then these policy points all behave in an updateful manner with respect to this like binary information.
Yeah, that's the case for influence no influence backwards. But what about like you said that there's another situation of no influence forwards. I don't fully understand.
Oh, maybe I misspoke. Yeah, you said backwards, and I thought you said like only influence backwards as
Oh,
opposed to no influence backwards. And so I think I
okay.
just misheard you.
So we're describing the same
Yeah.
thing. Okay.
Okay. So now I'm just going like, this is kind of a big picture slide of like, what's the project in this section? And now I'm going into more nitty gritty details of what kind of coherence conditions we might want to enforce in order to get this sort of result in the case of computational uncertainty. So, and I think, yeah, we've kind of like talked about a lot of these things to some extent earlier. So maybe this part will go fast. But so we have propositional coherence. One way that we can imagine setting up a logical inductor is, and this is the way that it was set up in like the first draft of the paper, not the public draft of the paper, but an earlier draft, is that we have one betting table per proposition. Traders put money on yes or no, indicating their bets for or against that proposition. And then the house's job is to set odds so that the ratio of money set down on either sides equals the odds. So if the house offers 2-to-1 odds against some proposition, then if I'm getting my direction right, that means that the house is promising that you can double your money if you bet for that proposition, and it comes out true. And what the house's job is to make sure that if it offers those 2-to-1 odds, then somebody else is going to put down that money. Sorry, not double your money, triple your money at 2-to-1 odds. And so somebody else needs to put down double your money so that if you win that bet, then what you take is triple your money so that the house doesn't have to pony up any money. The house is setting the odds so that the traders are just trading with each other, so that the house doesn't have risk. And yeah.
So I'm not sure. Like I understand that this is the this is the usual function of the house, but I don't understand how this relates to the logical induction criterion. In that, like no trader is guaranteed to have unbounded profit.
Yeah. So I'm describing the logical induction algorithm, or rather a like slightly modified version of the logical induction algorithm, as opposed to the criterion. So like, yeah, the algorithm shows that there exist things that satisfy the criterion. And the basic idea of how this relates to the criterion is that we can see that it's in the logical induction algorithm, we're setting up this virtual market where we control the wealth of all the traders and we assign them a particular starting wealth. And then we're saying, we make this construction such that with respect to this virtual market, the house doesn't lose any money, or whether because there's like an epsilon rounding thing in some places, the house could lose a very small amount of money, but it loses
Okay.
and then
Yeah.
the criterion, we're saying, well, now consider like an arbitrary trader approaches the house. We no longer control what the market makeup is. There's just this house that we've constructed from our simulated market, and then some trader approaches and makes bets somehow, and they can have a starting wealth that's different than the one we gave them in our simulated market, and so on. But we're saying that the loss of the house is bounded over here. The house can't lose arbitrarily much money to the trader because that trader has a copy over here in the simulated market. And so if they kept making money, eventually they would have all of the money in the market minus some epsilon for everybody else, and we would just be like paying good attention to that guy. That trader would be controlling all the prices, and so then this one over here in reality is not given any opportunity. It doesn't have any edge, doesn't have any way to make money from the market, because the market is just like setting prices in a way that completely is set by what this trader's beliefs are.
Sorry, if I understood the question of Norman correctly, and I also now have this formulation of question myself, is that the market you described, the first, like the ones that just balances out the money of the traders, is not like correlated with this virtual logical induction market. Like this market is fully determined by the traders who are trading there, and it's not controlled by this logical induction criterion. So how does this relation works? Like this is completely determined by the traders there, and not the virtual traders.
Yeah, thanks, Roman. And I think my current understanding is that this virtual or simulated market Abram is referring to corresponds to the super trader that's constructed in section 5. So there it is proved that this super trader would represent represent the combined power of all the traders, or like the power of any trader would be encapsulated in this super trader. So I think I just didn't get Abram's picture of like a simulated market previously, but now that I think of it, I think that's a good way to think of it this way. So personally, I don't have a question now, but Roman, if you want to continue to ask, it's Did that clarify for you?
Not in particular. Like I didn't quite read enough of the paper to understand like what do you mean by super trader, but I kind of get the picture. Like I don't understand in full detail, but I get what you're trying to say.
Okay.
Okay, so you didn't have a remaining question?
Me or
Roman? All right, so yeah, what I'm trying to do here is say like a market that's set up like this with one trading table per proposition, we can still design it such that it will converge towards respecting propositional coherence rules, such as the probability of any propositional tautology equals 1, and the If A and B are mutually inconsistent, then the probability of A or B equals the probability of A plus the probability of B. I should be saying the price rather than the probability, but kind of same thing. Because we put in place special arbitrage rules, so this is like if I bet, so let's say that the proposition X has price 0.8 and the proposition not X, which is a different proposition, has price 0.8 as well. Then I can put $1 on the table against proposition X and $1 on the table against proposition not X. Because I'm like, well, one of them is too high. Like, I don't know which one, but one of them has got to be lower. And then in this version of logical induction, which hasn't been published because it was a previous draft of the paper, there's a special rule where the House says, oh, okay, so I see you put money down on this arbitrageable case where like the probability of X plus the probability of not X sum to more than 1. So, and you're like trying to bring that probability down, which is good. So I kind of know you're good for it. Like no matter what the prices are the next day, I consider you to have made money because either X is true and not X is false, or X is false and not X is true. And either way, you've bought you've bought more payoff than you bought it with. So you've like made money in either of these two cases that we think of as eventually coming true. And so then the House just considers you to have made that much money. And so in that version of logical induction, then eventually we become propositionally coherent. The market learns to be propositionally coherent. But then alternatively, and this is the version in the logical induction paper, we can enforce propositional coherence right away. And so I visualize this as we have one big table where instead of like just like yes or no on individual tables, we have the positions on the table corresponding to the 2 to the n Boolean combinations of our n propositions. And so in order to put money down on proposition 2 being true, instead of just doing that, I have to identify, okay, like here's the subset of worlds where proposition 2 comes true, and then I spread my money around on those table slots. And so here we're kind of forced to have a coherent probability distribution instead of just eventually arriving at it in the limit.
Sorry, but
Yeah.
I believe that the in the limit case is one in the logical induction paper.
Oh yeah.
And the latter case, you said the opposite. So
Yeah. Okay. Well, maybe this is where I'm embarrassed because I didn't adequately review the paper before giving the lecture. But doesn't it have these like worlds where you put down the money individually?
Okay. At least like I'm not sure about the latter case either. But at least like what I know is that the non big like converging towards respecting propositional coherence is a property of the original logical inductor. Because if it doesn't do that, then it will lose like an unbounded amount of money
Yeah.
by a trader continually arbitraging on those A and not A.
There is a theorem, limit coherence, that is saying something like, if it is provable that phi and psi, then probability on the limit of phi or psi is sum of the probabilities of sum of the limit of the probabilities of phi and psi. So this thing is proved from the logical induction criterion, if that helps to determine what are you talking like, which one is the actually published one.
Yeah.
Right. Yeah. Yes. And as for the big betting table on worlds, Abram, could you elaborate a bit on what this actually refers to? Like, what are the Boolean combinations? Is it that there are n propositions and each world is like 1-0, like the truth, assigning a truth value to each of the n propositions, so that there are 2 to the n.
Right. Yeah. And I mean, I think we also like, we eliminate the worlds that are ruled out by the deductive process. So actually there are somewhat less worlds because the deductive process will prove some theorems that rule out. But basically you can think like, yeah, there's 2 in worlds, and that's like all of the propositions, proposition 1, proposition 2, ... proposition n, are decided true or false in each of these worlds. And then the traders make bets by specifying what worlds they want to put money down in.
How does this enforce propositional coherence?
So in the same way that for these individual tables, if I put $5 down on yes and you put $10 down on no, then we can think of this as probability mass. We can think of it like divide by 15 and say like, this is 1/3 on yes and 2/3 on no. And we've normalized it. It's now like a probability distribution on this very trivial sigma algebra that just has yes and no. Similarly, over here, if we just look at all the money that's on the table, and then we like divide by that amount of money, then we have probabilities on each world which sum to 1. And so we've got a probability distribution over these worlds. And each world is a consistent Boolean possibility. And so if we want to know the probability of something like A or B, we're just like summing up all these particular probabilities.
Can I ask what does it mean? Sorry, yeah, you first.
Yeah, please, Roman. It's okay.
Okay. Can I clarify what
Actually, I see you, Roman, but go ahead, Roman.
Oh, what do you mean? Okay. Can I clarify what does it mean to have a consistent Boolean world? Like, does it mean to, like, we have some set of rationality constraints on, like, you can't have phi and no phi both be true in that world, or something like that?
Right,
like,
yeah.
Wouldn't it just amount to the whole mass figured out? Like, if you just do enough of rationality constraints, like, what does it mean to have? Yeah. so Boolean consistency only means that like phi and no phi can be true in one world. Can be both true in one world.
Right. Yeah.
Right?
This is what I was aligning, and this is probably the difference. This is probably the mistake I'm making in terms of the version of in the paper. So I think the version in the paper, a world is just any Boolean combination of the propositions being true or false. With those worlds that the deductive process has being knocked out and not allowed to invest in them anymore. But that still allows there to be a world, like let's say world 3, like if proposition 1 is X and proposition 2 is not X, then world 3 could start out by saying X is true and not X is true, and then ... And so it could still be propositionally inconsistent because the deductive process has not yet proved the theorem that we can't have both X and not X. And so what I should have said here is that we can enforce propositional consistency in a computable way because we can computably, like by fiat, we could say that the deductive process does indeed rule out all of these propositionally inconsistent worlds. And
Eventually.
No. Like we can specify on each day, like because propositional consistency is decidable, and we only are dealing with a finite number of sentences here. And so we can just check every single world and make sure that it's propositionally consistent. And so for the actual logical induction paper, it's eventually, but we can just make it like right away by saying, well, we just check and we rule out the propositionally inconsistent worlds.
And the logical non-omniscience comes from the fact that we only have n propositions.
Also, it comes from the fact, like, yes, that, but also the fact that I'm only enforcing logical omniscience with respect to propositional consistency, meaning there's still first order rules of logic that are not being respected. There's still axioms of piano arithmetic that are not being respected, because those logics are not decidable at finite time. We could take arbitrarily long to find the proofs in those logics, and so those come into the deductive process slowly.
Oh, I see. Yeah, thank you. That clarified it.
Okay, so apologies for my confusion. Are there any further questions on this slide?
It's not like a question, but I'm just kind of wondering. This seems to be not a lot nicer. So why didn't the logical induction paper already do this? Would this cause some difficulty?
At some problem
later?
At some point when Scott was working on the paper, he told me that he was doing this, which is why I believed that it was doing this. So yeah, I'm not sure why the decision was ultimately made.
Maybe it's because it seems more powerful for propositional coherence to emerge from the process. Like,
yeah, and I think it's also like, maybe I'm gonna skip some slides here just for illustration. So like, yeah, this picture is now wrong. I apologize, but basically, like the logical inductors in general are not propositionally coherent, and so it's kind of more illustrative to investigate that case, right? Like you do not need to be propositionally coherent in order to satisfy the logical induction criterion. And so it makes a lot of sense to focus on proving that theorem that holds for logical inductors in general.
Yes, it's like they're trying to build this most general criterion possible for their like heuristic good properties.
Yeah.
Whole like without even only with asymptotic. No. What I'm saying, yeah. I'll stop here. Okay.
All right.
So shall we continue? Or
yeah. So propositional coherence, basically, I think of it as letting you work with conditional probabilities without worrying too much about them doing something funny, because like you have the and is working as expected in the conditional probabilities, but it doesn't give us everything we need for this decomposition that I highlighted earlier. So it seems as if we need some analogous type of coherence for expectations, not only for propositions. So there's several different things that we could try here. We could do something analogous to this big table approach, where instead of just enforcing propositional coherence by looking at these propositional worlds, we also enforce constraints related to real valued variables. And so then instead of imagining this big table specifying all the propositional worlds, we would also imagine a world to specify like what value a real valued variable has, or rather like we put them in bins so that we still have a finite number of bins, so like some range for the values. And so now instead of 2 to the n, so like we have all these Boolean dimensions, we would further think of it as divided into like, for all of the real valued variables that we're considering, we divide it into some level of granularity so that we have some little epsilon ranges, and a world has to be located in each of these. And so that's something that might be worth considering, and Martin Soto has some notes on that I've shared with you guys, but I'm going to sketch an approach based on the Jeffrey Volcker axioms. To try to get this kind of coherence that we need for this equation to work.
So sorry. Is it okay if we backtrack to return to the last thing we're discussing? Because I think I realized why the paper is doing it this way.
Okay.
Yeah. So you could not a world in the formalism of the paper has a truth value for every proposition.
Yeah.
So you cannot check that the world is propositionally consistent, like the full world is propositionally consistent computably. You can only check that when it's restricted on like a set of finite sentences, when the truth values of the world.
Yeah.
And the deductive process in the paper is growing each day.
Yeah.
So in a sense, checking whether worlds are propositionally coherent when restricting to the sentences of the deductive process is kind of like the best you could do. You could of course check with respect to a faster growing thing, but you couldn't. Yeah. So in light of this, I'm not sure what you mean by enforcing an independent notion of propositional consistency on the worlds, like
Yeah, so
independent of the deductive process.
when I say world here, I mean one of these 2 to the n Boolean combinations of only the sentences that we're looking at on that day. And so we can distinguish between propositional coherence just on the sentences that are in the market on that day versus then trying to extend it out to infinitely many sentences. And so, yeah, I'm saying we can computably get like propositional coherence on the world in that day, and then for the rest of the sentences, all the sentences that are not yet in the market, we can also enforce propositional coherence, but in some like dumber way, where we just assign like atomic propositions probability 0.5, and then conjunctions of atomic propositions are just like multiplying out the probabilities.
Mm-hmm. Yes, I think I get it, but how is it actually going to work? Because like the sentences on the market is on that day is defined by the traders trying to trade on these sentences, right?
Yeah.
And traders trade on these sentences by trying to bet on worlds.
Mm-hmm.
And now what you're trying to do is only allow the traders to bet on those worlds that are propositionally consistent with respect to those sentences.
Yeah.
So it seems that there needs to be an independent notion of like traders trying to bet on things, independent of like putting bets on worlds.
Right. There needs to be like a notation that they use to make their bets, something like that. Like when we computationally specify what kind of object the traders are, we have to spell out how they're making bets. But
Yes.
checking whether they're betting on a propositionally coherent world is something we can do in, well, exponential time, but it's computable.
Oh, okay. Oh, yeah. Okay. So it okay. I think it works. Like I remember. Sorry. Like in the formalism in the paper, the traders are like the traders are these like combinations of sentences with their betting on sentences together, like multiplied by the weight, like by the money. So yes, I think you could just check what those sentences are.
Yeah.
But these sentences might have like one sentence might represent a propositionally inconsistent world.
Right.
That's possible. And you want to rule this, then this trader is out.
Yeah, like this is like burning money. Like if you sink money into a propositionally inconsistent world, you've just lost the money.
The rule, like the rule of the market is this.
Yeah, I think that would make sense. I'm kind of, I'm just sketching something I think would work. I don't like it. Yeah.
Okay. Yeah. Yeah. This. Yeah. It seems that like we could try to clarify this, or maybe to review some of Martin's notes. I think he did like some clarification.
Yeah.
On this. Okay. Thanks. Sorry for the interruption.
Mateusz, did you want to voice something?
Voice? No.
Okay. I haven't read all of what you wrote. Okay. So, yeah, I'm going to sketch an approach based on the Jeffrey Bulker axioms. So, Jeffrey Bulker preference structures are, to give a little bit of background here, it's like, first we had like the V&M axioms, which are still the axioms of rationality that everybody thinks of, but are not that great in the sense that the V&M axioms just assume that probabilities are given. So it just kind of assumes like you can make these probabilistic mixtures of any outcomes, and then it only establishes like, you should use utility given that we have these probabilities. And so Savage around 1950 was like, well, the foundations of expected utility theory assume probability is given. And conversely, the foundations of probability theory assume expected utility theory is given, because the Dutch book arguments assume that you're willing to act according to expected utility in order to get you to make these bets by the Dutch book argument. So actually, this is one big circular reasoning situation. And so that's not great. So Savage was like, okay, we need to refound the foundations of statistics on a theorem that derives expected utility theory and probability theory from some plausible rational axioms, so that we have a foundation instead of circular reasoning. And so that was the Savage axioms, and the Savage's theorem is like this successor to the V&M axioms. But then arguably Savage's framework has some weird issues with it. Not to get into too much detail, but it's like, it makes the matters of belief and the matters of preference two completely distinct domains. And so if it makes sense to say what you believe about something, then it doesn't make sense to say what you prefer about that thing, and vice versa. If it makes sense to say what you prefer about something, then it doesn't make sense to talk about your beliefs about that thing. So the Jeffrey Bulker preference structures are specifically addressing that, and they're putting these together. They're saying like, there's just going to be this event algebra, this Boolean algebra, that is like all the stuff in the world that we think about. And we're going to have the probability on those propositions and also the expected utility defined on those propositions coming out of some rationality axioms, which I haven't written down here. But they have a similar flavor to the V&M axioms, as the Savages also have like a similar flavor to the V&M axioms. But so then what we get out of these axioms is this representation theorem that says, indeed, we can represent rational agents as having this probability-like thing on events, which doesn't fully follow the Kolmogorov axioms, but minus countable additivity. So specifically have the probability of top is going to be 1, and if two things are mutually exclusive, then their probabilities sum together. And then the value of a proposition or the value of an event is it acts like an expected utility, by which I mean it follows this averaging rule where if A and B are mutually exclusive, then the expected utility of A or B equals the expected utility of A times its probability plus the expected utility of B times its probability normalized by the sum of the two probabilities. Yeah, Roman?
Why isn't denominator 1? Like, it's the previous axiom, isn't it?
So A and B are mutually exclusive, but not necessarily jointly exhaustive. So
they are jointly exhaustive. Like, it either A or B. Like, if A or B, if it is A and B can't coexist.
Yeah.
Oh.
So
sorry.
A,
Yeah, I get it. Sorry. Yeah.
okay. But just to give a concrete example, A could be that some number equals to 1. B could be that number equals 2. And then we can have a C that's like that number does not equal 1 or 2. And then A, B, C would sum to 1, but A and B don't necessarily sum to 1. Mateusz?
Does Jeffrey Walker use the value of like the top element as something of truth as something like the default, like a 0 in the utility function or something?
Yeah, that's a good way to think about it, because it's just the average of everything.
Yeah, because I think he was using this like something like that in the logic of decision when I was reading this some time ago.
Yeah. Yeah, so like the value of top is just like, well, how good do you expect things to be? Not conditioning on anything. And then the value of bottom, importantly, is not defined. So like the probability of bottom is defined to be 0 if you combine these two constraints. But the value of bottom is not defined because, I mean, from a classical standpoint, that's kind of like trying to condition on a probability 0 event. Although here we don't have that kind of justification, but yeah.
Does it also mean, so what about other propositions that currently are like assumed to have probability 0? Can you have value attached to them? Or is it also undefined?
Yeah, I think it's a good question. If I recall correctly, that's still going to be defined. But I could be misremembering on that. I think this is the only one that's not defined.
Okay. I mean, this would mean that the non-expected actual utility is undefined because you divide by 0 if you want to treat it like that.
Right, like this formula is going to be undefined.
Yeah.
Yeah. Yeah, good question. I think it's going to be defined to be just something, but I'm not 100% confident in that.
Oh, I just realized, like, shouldn't in this like expected utility like formula, in the numerator, PB and PA be on the opposite sides?
What?
Shouldn't it be PB times VA plus PA plus PA VB?
I don't think so. So it's like I have a cake. Somebody asks, how good is the cake? There's like a chocolate side and a vanilla side. And I split them into the chocolate side and the vanilla side. And I'm like, well,
Okay.
how good is the chocolate side times how big is it? And then how good is the vanilla side times how big is it? And then I'm like,
Okay. Yeah, I think I was confused about how it was like kind of derived, but never mind.
Okay. Yeah, and so you don't have any underlying utility function. That's why this is called V instead of like using the normal expectation symbol, because you just have V. You don't need to postulate a utility of which we are taking the expectation. Instead, you just have these values that act as if they were expected utilities. So it's kind of like the difference between like pointless topology versus point set topology. We're not directly dealing with these like worlds that are like outcomes. Instead, we're directly dealing with an event algebra and defining everything on that. And then this is just a kind of interesting technical aside. So Scott Garabrandt observed that this can be thought of as a finitely additive vector valued measure. So instead of thinking of all of this, we can just think of like there's a two-dimensional vector space. And so the vectors J, the vector associated with an event can be constructed as the probability of the event, comma, the value of the event times the probability. And then we get that these vectors decompose nicely into a vector valued measure. And so equivalently, you could think of this whole thing as instead of the Jeffrey-Bulker axioms, we just have vector valued measures. And then when we consider an event, we're trying to maximize the slope. Like if we're given a choice, then we choose the thing with highest slope, because slope is rise over run. And here the rise is value times probability and the run is probability. So we're just like doing this kind of rotational maximization thing that's kind of neat. But that's not so critical here. It's just kind of interesting. Because in a kind of more unified framework to just say it's a vector valued measure.
I'm a bit confused as to like how this V is actually applied in practice.
Yeah.
Like I would have a value for like V of truth. Like I don't know what it's called, the T, like the whole space.
Top, true.
Okay, top, yeah. And so that would be like the expected utility if I don't do anything. I just let things happen, then it will follow.
So I would say it's the expected utility if you do what you do. Like you still might expect yourself to do something, but you're not conditioning on doing any particular thing. You're just like, well, what's the expected utility conditioning on nothing? So I might be like playing chess and I expect myself to make some move, but I like haven't yet thought about what move I'm going to make. Then V of top is just like the average expected value.
We haven't like clearly defined what the decision theory in that formalism, so I don't think it yet makes sense to talk about that.
Yeah, that's fair too.
Okay.
Yeah. So the way that Jeffrey talked about the decision procedure is you're choosing between events somehow. Like you have some choice between events, and the events, they have a value. So it's like you have certain events that you can actuate, that you can make real. And those are like your actions. But of course, he wasn't trying to do updateless decision theory. So, yeah, any further questions or comments?
So this P, actually, I don't think it could be equated to the P in updateless, in the prior in updateless decision theory.
Oh, in what way?
So if I say that I'm updateless on this P, I'm saying that I so I'm actually thinking about like the case where you could behave as if you're updatefully, provided that you don't have a causal and retrocausal impact.
Mm-hmm.
So how would that work under this formalism? Because of the
Yeah, I guess I'm kind of not seeing the problem. Like if you just take this P to be the Jeffrey Volker P, and then take this V to be the Jeffrey Volker V, or like, yeah, substitute V here. Why doesn't this just the same analysis make sense? Of course, we have to define what conditional V is, but I think that's fine.
I think you don't even need to do that. Like it just V of two events. Like
oh yeah, you're right, because we don't need the U. Yeah, it's just V of phi and O. Yeah, like phi conjunction O. And then I think this whole analysis still makes sense.
It depends on whether you take the view of each. Yeah, I think that it's the same issue. Like if you take the view of each new observation partitioning the world into further, like making further, more fine-grained events on this sigma algebra, on this Boolean algebra, then your P would continue to jump. But that's gives you a good way to formalize like the bottom half of the slide you're currently showing.
Right.
On the other hand, if you take observations to be like the full history, then I'm not sure whether I understand.
Yeah, then this intermediate point can't be an observation. It has to be just some partition. Some description of the world, but not one that we observe at some point.
Yes.
And then I think it still kind of makes sense, but this is misleading in that I've drawn something that's supposed to be like a decision tree, but it's not like a decision tree because this isn't like a decision node. So yeah, I haven't done all my homework here for this part. I agree that needs to be spelled out better.
I still sorry, I still don't see how you could take each observation to be the full history and use it to define, like translate it into events. So it's like what would be an event, like a event A, what's that called? Sorry, A or B. Yeah, the event A or B
Yeah, like
would
if
be like two histories, history A or history B.
I feel like I want to be careful here about what exactly do we mean by take the observations to be the full history before I can quite answer your question. Like, so imagine that I'm seeing a sequence of bits, and at every time step I see another bit. Then, and like I treat this as my observation. I observe like I need to make a distinction between, do I observe the proposition like 10111 or whatever, which is consistent with the proposition that says like 1011111, like adding more bits is just a refinement? Or do I observe the proposition that says like I see 10111, which is inconsistent with I see 1011111, because I don't see that additional one. So are you imagining, when you say the observations are the full history, are you imagining the first or the second scenario where like observations, like any valid observation is inconsistent with any other valid observation? Or are you imagining the version where extensions of an observation are consistent with prefixes of them?
So actually, like the only version of this correspondence that I could intuitively make sense of, like in my mind now, is like observing 10111 would be the union of observing all further histories, like observing 1011111 or 11011. So in this way, you have a like a infinitely a filtrated structure that points towards the future infinitely.
Okay. Yeah.
Yeah.
So in that case, then this is like a real decision tree, because this node could correspond to 10111, and then this node corresponds to 1011111, and this is a partition. Like, I guess this node just represents like the negation, like all the other paths or something. Maybe I should, just this is observing a 0, this is observing a 1, but yeah, you get the idea. And so in that case, I think, well, sorry, what was your question about this?
In that case, in that case, we've got to modify the current, like the picture you have here, right? Because like the P we use at each stage of this like observation action sequence would be like each stage we would use a more refined P, but that doesn't mean we're being updateful on the P, because like we could have a P like in the Jeffrey Volker formalism, we have a P that's defined for like the infinitely like filtrated sigma algebra, Boolean algebra already, and we're using that and being updated about it.
Yeah,
I think
but-
intuitively this seems quite powerful, like this way of doing things. But yes,
but
that's
the
my
idea
opinion.
here is we like it's not that we're being updateful, but that we're decomposing the update. This is like the expectation that updateless decision theory needs to take with some phi, depending on which version of UDT we're using. And then we're decomposing that expectation into these like updateful portions, in the sense that it's like a like we're conditioning on observations now. So we're saying like, what's the expected utility conditioning on some observation, rather than only conditioning on whatever our action notion is. And then saying like, we behave updatefully if, considering this decomposition, all the other things are negligible. All the other things that would influence this expected value can be kind of ripped away, and we're left with the difference between two different actions that we could take, depending only on this term where O equals the actual observation that we're being faced with when we're considering that action.
Yes. So okay. So I think you're pointing out my mistake. In this way of decomposition, we are only decomposition on the observation at the current stage. So it doesn't really matter whether the observation we're using a graded structure or like other things.
I think so.
Yeah, like what all that I've said is compatible with what is written down here.
Yeah, I think so.
Okay.
Although
Yeah, I agree.
Yeah, we may have other reasons for preferring one choice or another, but yeah, I think this is like a fairly generic setup.
Okay. But it still like if you want to say like this bottom half, then it will make a difference.
Yeah, like it'll make a difference to the details of that. Yeah.
Yeah.
So where was I? Okay, Jeffrey Booker. So, oh, what time do we have? Okay, so maybe this is just a good time to stop.
Are you satisfied with this pace?
Yeah,
or like
what
could we do that?
I kind of expected to get to Bayesian logical induction, since we just had the SAM lecture, but I guess I underestimated the number of slides between. But yeah, I mean, I think it's okay. I think the discussion is good.
Can I have a meta request?
Yeah.
If like, is it possible? Is it an easy thing to do to turn on captions and have them in the recording? Like,
Oh, I thought I did that actually.
You might, like, I don't know, like I do not see them in the Dropbox recordings.
So
like,
every time I turn on a recording, I think I'm hit with a question of like, what language do you want the captions to be in? So that's unfortunate and surprising to me.
Like, I don't know, maybe I'm looking in the wrong place.
I'm looking in the settings right now, and it's saying like language for captions, English.
Well, I'm not sure that like you could. It's that like for everybody who want to turn on captions in their own like view, the caption would be English, but not that they would show up in the recording. Like if it's something easy to do, like I'm asking you to do it. If it's something not so easy to do, don't bother.
Okay, so I can turn on that right now. Maybe I need to do that all the time and it'll just show up in the recording.
I don't know.
Can
If it's
Do you
easily
see
doable,
when
then
I turn
I
it
would
on for
appreciate it.
everyone or just for myself? By the way, I turned on captions on the bottom. There's a setting on the bottom of my screen, and now I'm seeing captions. Do you see them?
I do not see them. Like I
Okay.
can turn on them myself, and then I will see them.
Maybe if I just have this going, then it will be in the recording since it's like recording my screen. I'm not sure.
Well, we already testing it. Like if it will show up in this recording. So yeah, thank you.
All right. All right. Take care, everyone.
Thank you. Goodbye.
Thank you.
Yeah, thanks.